Welcome to some further exploring with cosine and sine. The first thing that I want to take a look at is just a brief review of SOHCAHTOA, which a lot of you have said that you've learned either in geometry or algebra 2. Now, whether or not you remember what it means might be another thing. This is just dipping your toe into the pool of trigonometry. So SOHCAHTOA is like the building blocks of trig, the ideas of which we have looked at in the first video with cosine and sine and angle measure. However, if we're taking a look at any angle, theta, when we make a right triangle, we of course have a hypotenuse, which is opposite from the right angle. Then the two legs on this right triangle are called either the opposite or the adjacent. Opposite literally meaning it's opposite from that theta, and adjacent meaning next to. Now, yes, the hypotenuse is also next to the angle in question, but since it's the hypotenuse, it's never classified as the adjacent side, even though technically it is next to it. The adjacent side is the leg that is next to it. So SOHCAHTOA is the easy way to remember that sine is the ratio opposite over hypotenuse. The cosine of that angle theta is similar to sine, but it's adjacent over hypotenuse. And then tangent, which we'll get into later, is opposite divided by adjacent. Now, sine, cosine, and tangent are simply just ratios of the side lengths of the triangle formed with a particular angle. And even if we were to extend this triangle so that it went beyond the unit circle or whatever we're talking about, because sine, cosine, and also tangent are just ratios, they would stay the same. So we have something that we could draw if we extended this triangle out further. It would be a similar triangle, and this angle would not change. So no matter how much we extend this triangle or even shrink it, if it stays proportionate to the original triangle, the sine, the cosine, and the tangent of that angle theta would not change. The reason that we care so much about the unit circle, well, one of those reasons, is because it's sort of an easy ratio to take a look at, right? The radius of any one of these right triangles that we can draw, or the hypotenuse of that triangle, is just 1. So if we take a look particularly at pi over 6, which we've already done, and we were to draw that right triangle here, and remember pi over 6 is just a 30-degree angle, so I'll just write it as 30 degrees. And if we create that right triangle there, of course, our radius or the hypotenuse of our right triangle is 1. We've already determined that the opposite side length of it is 1/2, and that the adjacent is root 3 over 2. Now we can also use the Pythagorean theorem to say that this side squared plus 1/2 squared would equal 1, or 1 squared. But the other cool thing is that we have determined the cosine and the sine of this pi over 6 or 30-degree angle. So if we take a look at this nifty little chart here, which I do recommend that you write down, our 30-degree angle, or pi over 6 in radians, the cosine is of course the x value, and the sine is the y value for any point on our unit circle that is along the terminal side of our angle. So all of these things are sort of coming together. Now, of course, I'm drawing this in the first quadrant because everything's positive. It's sort of like the easiest way to draw it. But if we look at any of the pi over 6 family, the cosine is either positive or negative root 3 over 2, those 4 spots that have over 6, and the sine value of any of those pi over 6 is either positive or negative 1/2. How do we know whether it's going to be positive or negative? Well, if we know that cosine is the x value and sine is the y value, then just by using our knowledge of how coordinate graphs work, or coordinate planes rather, we know that x is positive when we move to the right. So in quadrants 1 and 4, note that every single x value is positive. Therefore, the cosine is positive to the right of the y-axis in quadrants 1 and 4. Cosine is negative in these other 2 quadrants because we're moving to the left for the x. Then sine of any theta, any angle rather, is of course the y value, and y is positive up top, up here when we're going up. So in quadrants 1 and 2, all of our y coordinates, or the sines of all these thetas up here, are positive. And then when we go down in quadrants 3 and 4, sine is always negative. So depending on where your angle is, when you know the quadrant that you're in, you can determine whether or not the cosine and or sine will be positive or negative. Now, if you're on an angle that's right on an axis and not in any quadrant, so 0, pi over 2, pi, 3 pi over 2, and 2 pi, and then if you keep going around, just knowing where you're at will allow you to know whether or not your cosine or sine is positive or negative. So for instance, pi over 2, if you know that pi over 2 is going straight up, you know that your cosine is 0 because you haven't moved left or right at all, but your sine is 1 because you've moved straight up 1 unit. Whereas if we're talking about pi, which is all the way to the left over here at 180 degrees, since we're moving 1 unit left, the cosine is negative 1, but the sine is nothing, it's 0, because we haven't moved up or down at all. So in conclusion, in this first part here, do be sure that you have a copy of the unit circle. You can either use the one from your textbook, which is where I got this one, or you can just Google search the unit circle PDF so you have one to reference. Also, be sure that you write this down. It's a nice little organized table of the most common angles around the unit circle as well as their cosine and sine values. And if you do not have SOHCAHTOA memorized or recall what it means, just be sure that you write down what these three ratios mean. Remember, sine, cosine, and tangent of any angle theta, they're just the ratios of the side lengths of the right triangle formed. The first examples that we'll take a look at are basically solving. So we're sort of working backwards to find the angle or t value that provides the given cosine or sine value. So let's use our unit circle just for reference. So in our first example, I've moved things around a little bit, we want to know all of the angles theta such that the cosine of that angle theta is 1/2. Well, cosine is our x value, so we want to look on our unit circle and look at every single spot that our x value is 1/2. Well, that happens in the pi over 3 family, but not at every pi over 3. At 2 pi over 3, the cosine's negative 1/2, so that wouldn't work. And down here at this 4 pi over 3, again, we're negative. But here, at 5 pi over 3, we have also satisfied the answer here. Our cosine is 1/2. So our answers appear to be pi over 3 and 5 pi over 3. Now, are those the only two spots? Well, the unit circle is infinite. We can keep going around it. So if we start at pi over 3, what about if we add an entire 2 pi or 6 pi over 3, right? Just another way of saying 2 pi. What if we add that entire thing and we're at 7 pi over 3, the same spot, a coterminal angle? Then what about if we did it again and we were at, let's see, 7 pi over 3 plus another 6 pi over 3, 13 pi over 3, and so on. We could infinitely go around and keep ending up at the same spot where the cosine of that angle is in fact still 1/2. The way that we write that answer is we start with the angle that we want, which was pi over 3, but then we want to keep adding 2 pi a k amount of times where k is an integer. So we can add it one time and go around again once. We can add 2 pi twice where k is 2, and we can go around again. We can actually add 2 pi a -1 amount of times and go around in the negative direction. So k is just an integer, k could be 0. So this is how we answer that first part of our question. Then the second part was, what if we were at 5 pi over 3 and we did the exact same thing? So the way that we would write that one is very similar. Theta could also be 5 pi over 3 plus, of course, every time we go around, 2 pi k times, where k is an integer. So that has answered question number 1, to find all of the theta values, all of those angles such that the cosine of that angle is 1/2. Let's take a look at number 2, where we want to see all of the angles such that sine of that angle is -1/2. So if we take a look again at our unit circle, we want to look at all the spots where our y value is -1/2. So y is negative down in the lower two quadrants, quadrants 3 and 4. And sine is -1/2 here at 7 pi over 6. And it's also -1/2 here at 11 pi over 6. So we do have to answer these as two separate answers once more, because there's no way that we could get from 7 pi over 6 to 11 pi over 6 and then add the same amount and like get back to here. It's just disjointed. So because they're right next to each other, we have to answer as two separate answers. So all the theta equals 7 pi over 6 plus any time we go all the way around. Then same with 11 pi over 6. The sine is negative 1/2 at 11 pi over 6 plus anytime we go 2 pi k around, where k is an integer. So this is how we can write these two answers here for answering what theta could be, so that sine of theta is negative 1/2. The last one we'll take a look at is cosine of theta equals 0. So again, cosine is the x value. And so we take a look at our unit circle. Where is the x value? 0. Now 0 is an interesting one because it has to be on an axis. So the cosine is 0, or the x value is 0 here at pi over 2. And then like clockwork, down from 12 to 6 here at 3 pi over 2. Then if we keep going around, it's every half of the circle. The cosine is 0. So we start at pi over 2, and then how much do we have to add to get down here? Do we have to answer this as two separate answers, or can we fit it into one answer? We can fit this into one answer because we have to add the same amount each time to get back to each spot that we want. So if we start at pi over 2, we only have to add half of a circle, which is 1 whole pi, to get to our other answer. But then what if we kept going? We add another half a circle, or pi, to get here. If we keep going around, it's like clockwork. Every time we add pi, starting at pi over 2, we have another place where the cosine is 0. The way that we can write this one then is a little bit different, as only one answer. So we'll start with theta as pi over 2, but then we have to add pi to get to our next answer down here at 3 pi over 2. And if we keep doing that a k amount of times, where k is an integer, we will encompass all of the potential answers. So here's how we can write this answer here. And again, it's a little bit different than these two here because the answers for where theta was 1/2, or cosine of theta rather was 1/2, was pi over 3 and 5 pi over 3. And they were not an easy amount apart. So we couldn't add this amount and then add that same amount again and get back to where we wanted. They weren't like as symmetrical as the answers here for number 3. So that is why in number 3 we can answer it in like one fell swoop instead of having to answer in two separate theta equals. Okay, let's take a look at these other two questions here. We want to solve for t, and it's kind of the same idea, except it's just a different way of putting it. So we want to solve for t so that sine of t equals negative root 2 over 2. So again, let's take a look at our unit circle and see where is the sine, negative root 2 over 2. Sine is y value, and it's negative down here in the lower two quadrants. Well, it looks like sine of 5 pi over 4 is negative root 2 over 2, and same with 7 pi over 4. So those are our two answers for t. And then once again, it's not just at 5 pi over 4, it's all the infinite amount of times we could hit it, adding 2 pi every time. Same with 7 pi over 4. Here this looks a little bit weirder, but this is actually the same thing as saying k is an integer. This is k, and this is a part of, or is an element of, the integers. Z, or a boldface Z, by doing this double bar here on the Z, is the symbol for the integers. So this is just an alternate way that you can write it. It's totally fine to just write out in words k is an integer. Let's take a look at this last one here. We want to solve for t so that the cosine of t is 3. Now if we take a look at our unit circle, do you see anywhere where the cosine is 3? I do not, and neither will you. The largest cosine value that we actually end up having is 1, and the smallest cosine value that we end up having is negative 1, and that's because the radius of this circle here is just 1. So it's never going to extend past that. So there's actually no spot where the cosine, or the ratio of the adjacent over hypotenuse of the right triangle it forms, there's no time when that ratio is going to be 3. So we would say that this does not ever occur, or we can simply write no solution. In this next example, we want to see what would happen if we extended our unit circle and created another circle that has still the center at the origin 0, 0, but its radius is not 1. We still call this angle that's formed, though, when plotted in standard position, meaning that it starts at this side of the x-axis here from the origin and moves in this direction or this direction. So let's take a look at this Q value here. And this is just a general picture. This is the specific example up here. So we'll just take a look at it generally first. What we see is that the angle is not changing. Yes, we're extending the hypotenuse or the radius here. However, the x and y values are going to become larger, and the radius or the hypotenuse will no longer be 1, but their ratios will remain the same. So we can still use the idea of SOHCAHTOA and our understanding of this circle in order to find the sine and the cosine of this new theta. Now we'll go into specifics. Let's actually plot this Q, this specific Q, which is 4, -2. So it looks like it'll be somewhere around here. Then, of course, I'm going to extend and create a right triangle. And our theta that we have in here would be right here. Now, you could argue that this theta is really moving all the way around and ending up here, and that's totally fine. It could be an obtuse angle, but the terminal side is right here, and this would be the reference angle formed anyway, which is the acute angle that's formed closest to the x-axis. So either way, we're ending up at the coordinate point 4, -2. I knew that we ended up down here in quadrant 4 because we had to move 4 to the right and 2 down. So I knew that just because of the signs of the coordinate points. So we can actually label our side lengths. We know that this side length here is 4 and this one's 2. Yes, you could also write -2, but I like to just write distances as positive anyway, and I kind of took care of the negative here by showing what that coordinate point is. Now, in order to find sine and cosine of this theta, we use what we know about sine and cosine. I'll label this r because we don't know it yet, and it is the radius. We know that the sine and the cosine are SO and CA, so we know that the sine is opposite over hypotenuse, and the cosine is adjacent divided by hypotenuse. Now, we don't have the hypotenuse, or r, of this larger circle, but we can find it using the Pythagorean theorem. Using the Pythagorean theorem, I set it up down here. We have 4 squared plus 2 squared. Even if you did -2 in here, you'd still square it and get 4. So it doesn't really matter if you use the negative in the Pythagorean theorem. We'll end up with 20 equals our radius squared. And then when we take the square root of 20, we can break it down. We'll have root 4 times root 5, so we'll have 2 root 5. So we know that this side length here is 2 root 5. All right, now we can find the sine of theta. Sine is opposite over hypotenuse. So from theta here, our opposite is 2, and our hypotenuse is 2 root 5. So when I write that down, we'll have the sine of our theta is 2 over 2 root 5. Now, taking a look at where this theta is, because it is in our fourth quadrant, the sign is negative down there. You also could have gotten that by knowing that this is really -2. So we know that the sign down here, because we're in quadrant 4, the sign is negative. Now we can simplify a bit. So we have -1 over root 5 when we cancel the 2's. And of course, we do not like writing roots in our denominator, so we'll multiply the top and the bottom by root 5. When we do that, we'll get -root 5 over 5. And that's the sine of theta. Next, we'll do cosine of theta. Cosine is adjacent over hypotenuse. And the adjacent side length of our theta value here is 4. And of course, the hypotenuse, once again, is 2 root 5. And cosine, because we're moving to the right here for quadrant 4, cosine is positive. So we'll have 4 over 2 root 5. Simplifying, we'll have 2 over root 5. Then once again, we need to multiply the top and the bottom by root 5 to rationalize and write in a simplified manner. So we'll have 2 root 5 over 5. And so we have successfully found the sine of our angle and the cosine of our angle using the Pythagorean theorem and SOHCAHTOA. In these two problems here, we are given some clues about a certain angle theta, and then we need to find this other missing part. So in the first one, next to the orange star, we're given that the sine of some angle theta is -7 over 25, and that theta is in quadrant 4. We then need to figure out what the cosine of theta is. So I'm going to sketch this quickly. So here's our x and y axes, and then we have some angle, and it's all the way in quadrant 4. So if we go around, we end up somewhere over here. this very large angle. I'm just going to draw the reference angle in, which is the one closest to the x-axis. Then I make this right triangle. So our angle here, the one we're going to care about, is right in there. Yes, this entire angle is technically theta, but this reference angle will give us the same information. So the sine, once again, is the opposite over the hypotenuse. So from our angle theta, our opposite here is 7, or -7 in this case, and then our radius of our right triangle, or our hypotenuse, is 25. We need to find the cosine of theta. Cosine is adjacent over hypotenuse, so we do know that the cosine is something over 25. Let's find that something using the Pythagorean theorem. So we'll have that something, which I'll just call x, since it technically is the x value. So we'll call it x squared plus 7 or -7, however you want to play it, equals 25 squared. Either way, when we square either one of those 7s or -7, we'll get positive 49. Then 25 squared is 625. When we subtract 49, we will get 576. And the square root of that is plus or minus 24. I'm going to keep it as positive 24 in this case because it is a side length of our triangle. Now, because we're in quadrant 4, the sine is definitely negative, as was told here. So we know that, but the cosine is actually positive because over here we're moving to the right, and then of course down, but because we're moving to the right, the x value is positive. And since cosine is adjacent over hypotenuse, we'll have the cosine is positive 24 over 25. Our next example, next to the yellow star, we're given that the cosine of some angle theta is 4/9, and we're in quadrant 1 this time. We want to know what the sine of theta is. So we're in quadrant 1, and our cosine is 4/9, so I'll sketch something right here, and that's our angle theta. Now, cosine is adjacent over hypotenuse, so the adjacent side is 4, and the hypotenuse is 9. We want to find the sine of theta, and the sine of theta is the opposite side divided by the hypotenuse, which is 9. So we need to find the opposite side, and in this case, I'll call that y because why not? You can call it whatever you'd like, but because it's a vertical distance, I'm going to call it y. All right, let's do our Pythagorean theorem. We have 4 squared plus y squared equals 9 squared. So we'll have 16 plus y squared equals 81. When we subtract 16, we get y squared equals 65. And then when we take the square root of 65, we just get root 65. We cannot break it down anymore, so we'll leave it as root 65. Now the sine of theta we can find. It is opposite, which is root 65, divided by hypotenuse, which is 9. And because we're in quadrant 1, everything's positive there, so the sine is also positive just like the cosine is. So our final answer is that the sine of our angle theta is root 65 over 9. Here is the third of this type of problem. This one just looks a little bit different though because we have radicals already in our given information, as well as a different way of giving the quadrant that we're in. So let's break this down a little bit. Let's first look at the quadrant. We know that our angle is in between pi over 2 and pi. So if we do a quick sketch, we know that pi over 2 is 90 degrees, or up here, and then pi is over here at 180 degrees. So in between pi over 2 and pi is just another way of saying that we're in quadrant 2. So now we are given the information of theta, a sine of theta being 2 rad 5 over 5. If we draw a triangle over here with the reference angle theta, we know that sine is opposite over hypotenuse. So we know that our hypotenuse is 5, and our opposite side is 2 root 5. In order to find the cosine of this angle theta, we need to know the adjacent side length, and we can do that once again using the Pythagorean theorem. So setting up our Pythagorean theorem, I called our missing side length x since it's an x value, and then we need to square 2 root 5. That means squaring both parts, so it means we're squaring the 2 and we're squaring the root 5. Root 5 squared is just plain old 5. So we end up getting a 4 times a 5 there, so that term ends up being 20. So we'll have 20 plus x squared equals 25. giving us that x squared equals 5. And then when we take the square root of both sides, we'll technically get plus or minus root 5. Again, you can think about it either way. Because we are moving to the left and we're in quadrant 2, we do know that the x value is negative, and therefore the cosine will be negative over here. So I've replaced this with root 5. Again, I don't like putting the negative sign here because it is technically a length, but since we are moving to the left, we do know that in our final answer, the cosine of our angle theta is going to be adjacent over hypotenuse. So it's going to be negative root 5 over 5, again because we're in quadrant 2 and the cosine is negative there because cosine is x and we're moving to the left in quadrants 2 and 3. We will end this video with a couple main things that we just need to basically know in order to feel comfortable moving forward with trig. The first main thing is understanding the 5 main points on the unit circle. Those are 0, or where we start, then up here at pi over 2, or 90 degrees, over here halfway around at pi, down here at 3 pi over 2, and then finally, after one full revolution around, 2 pi radians. Next, we need to understand where each quadrant is. Now the quadrants make a C. So quadrant 1 is over here, 2, 3, and 4. So if we're told that we're in quadrant 1, another way of saying that is we could say that any angle theta is in between 0 and pi over 2. That's one way to say that you're in quadrant 1. In the previous example, we saw that theta was in between pi over 2 and pi, and therefore we that our angle was in quadrant 2. Quadrant 3 lies in between pi and 3 pi over 2, and quadrant 4 lies in between 3 pi over 2 and 2 pi. Next, the phrase all students take calculus, drawn in the order of the quadrants 1, 2, 3, and 4, is a phrase that students use to remember where the sine, the cosine, and the tangent are positive on the unit circle. So in quadrant 1, we have the word all. That literally means that the sine is positive, the cosine is positive, and the tangent is positive. We'll get to tangent shortly. So because of the word all, that literally means all 3 of them are positive. Now the other 3 use the first letter of the word. So in quadrant 2, the S, sine, that just means that the sine is positive. Because we're moving left and then up, the cosine is negative over here. The sine is positive because we're moving up. The tangent is negative because tangent is sine divided by cosine, and when they're opposite, one's positive and one's negative, that means the tangent's negative. So in quadrant 2, out of the 3, only the sine is positive. Down here in quadrant 3, take, or T, means that just the tangent is positive. The other 2 are negative. And over here in quadrant 4, C for calculus means that only the cosine is positive. So all students take calculus, drawn once again in the order of quadrants 1, 2, 3, and 4. The all means that all 3 are positive in quadrant 1. And then S, T, and C tell us which one is positive in those 3 quadrants. The others are, of course, negative. Of course, this is just a trick that you can use to help memorize this. If you just think about what cosine and sine are, and that cosine is the x value, and so it's positive when we move to the right, sine is the y value, and it's positive when we're moving up, and then the fact that tangent is sine divided by cosine, so it's positive when they're either both positive or both negative, you can use that as well. But if you prefer to use all students take calculus, feel free. And that actually concludes our exploration with cosine and sine.